Hello, students. Today we're working on applications of the base E and natural logarithms. So you'll find that this is similar to the lesson we did with common logarithms. And we have two formulas again we're going to look at. The first is interest that is continuously compounded. One that I'm more familiar with is A equals PE to the RT power, but that can also be written as P of t, so function notation, equals PE to the KT power. It's just different variables, but having these meanings. So here's the formula we're going to use for this problem. Sarah invests $1,000 in an account paying 3.4% annual interest, and it is compounded continuously. So we're going to use this formula. The amount that we start with is $1,000. That would be P. P stands for the principal amount, so 1,000. Your K is your percent, but written as a decimal. So 3.4% would be converted to 0.034 as a decimal. And then this problem, the number of years, how long or what would be the balance after 5 years. So 5 is your number of years. And so we have your formula, P of t, which is what we do not know, is equal to P. And then remember that E is a number. And then K, which is the 0.034, and that is multiplied by 5. Now, more than likely, as you put this into Desmos, you're going to want to put parentheses around that exponent. But we can go to Desmos and type that in. So 1,000 E, and then your exponent, parentheses, 0.034 times and 5 for 5 years. And you'll notice that then you get an amount that you could round to dollars and cents, 1185.30. The 4 would keep it at 30. So $1,185.30 when it says to round to the nearest cent. So let me get this working again. So 1,000, whoops, get it to draw. $1,185, I think that was, and 30 cents. I'm going to go back to Desmos and verify that. 1185.30, yes. All right, so that would be the amount of money that is now in the account after 5 years. All right, then it asks how long would it take the balance to triple in value. So that means we're going to use the same P, same starting amount, same K, but now we know a new P of t. So we're going to take P, which was $1,000. We're going to multiply that by 3, since it said how long would it take it to triple. And your new amount is going to be $3,000. So the P of t, 3,000, equals, and then the original amount, 1,000, E to the K, which is your decimal, and your unknown, your variable, is t. All right, so we want to divide first. We're going to divide by 1,000, and that will give us 3 equals e to our decimal 0.034t. At this point, we want to use a logarithm. So the exponent 0.034t equals, and then to get rid of the e, use natural log, and we're doing the natural log of the 3. So this is what you're taking the natural log of 3. To get your best chance at rounding properly, notice that you're going to have to divide both sides of this by 0.034. So you might want to go ahead and have that written down so that you can type that in. So it'll be the natural log of 3 divided by 0.034. Your natural log function in the functions box, ln of 3, and then dividing that by 0.034, and we get 32.312. We'll look to see what we're supposed to be rounding it to. It says round to the nearest tenth, so 32.3, and that would be 32.3 years. So 32.3 years that it would take for the amount in the account to triple. All right, and we have one other formula we're going to look at. It's very similar. It's P of t equals, I think the symbol that I need to explain is this one right here, P with a subscript of 0, and that stands for the initial value. So that 0 is time 0. It's at the beginning of time. So the beginning time, or the beginning balance at time 0 is what that's standing for. And so this one says find the time in years for 100 grams of a substance to decay to 50 grams with a decay constant of 3.5% per year. And it says to use this. So your K, which is your decimal, 3.5%. And so we'll write that, moving the decimal to the left twice. 0. We'll have to put in a 0, 0.035. Your initial amount, that P with a 0 subscript, is what it's starting with. So that would be 100 grams of the substance. And then the ending amount, what is it ending up with? Well, it's ending up with decaying to 50 grams. So that would be the ending amount. And so then we're going to solve it for t using our formula. So P of t was 50, and that equals P, which was 100. Remember, E is to the decimal 0.035, and then t being your variable. All right, so we will divide on both sides by the 100 to get the E by itself. So those are going to cancel. 50 divided by 100, you could check that out. That's a half, or 0.5. So 0.5 equals, and you have your e with your exponent, 0.035t. All right, now that'll be what we're solving for. So 0.035t equals, and then to get rid of e, we use a natural log. We're going to do the natural log of 0.5. And notice that we went from 100 to 50. So this is also known as half-life. You're taking the log of a half. And so one thing I failed to notice is that our formula is, and I just realized this, our formula has a negative in that exponent. So I should have put a negative right here as I was calculating this. This is a negative sign, and I'll need to carry that through on my example. So I have that negative sign. This is a negative sign. So that when I divide, which is going to be my next step, I'm going to divide both sides by negative 0.035. I'll end up with a positive answer, which needs to happen. So t equals, and then we'll do this division on Desmos. So it'll be the natural log of 0.5, and then that is divided by negative 0.035. Oops, I didn't use a decimal there. And we get 19.80. We'll look to see, it says round to the nearest integer. So 19.8 would round up to 20. And so this will round to 20, and that would be in years. So 20 years. All right, so those are a couple examples to help you out with the natural logarithm applications. Good luck with your homework on this.